In this series of videos, we've been thinking about the hidden Markov model, starting from the example of the observable Markov model, looking at how we reason with that and represent that, then doing some motivating examples of why we might want a hidden Markov model. We looked at examples of coin flips behind a curtain and drawing candy from different jars. We introduced the formalism of the mathematical representation of the hidden Markov model, and in this lecture, what I want to do is motivate different reasoning that we can do with that mathematical formalism. So to that end, what we're going to do is motivate the forward-backward algorithm. Now, as a reminder, this work is relying heavily on a paper by Rabiner, tutorial on hidden Markov models and selected applications in speech recognition. Let's imagine that you have a home, and in your home you have a domestic helper robot. Maybe that robot is vacuuming for you. Maybe that robot is a security robot. Maybe that robot is helping you find lost things when you're at work and you forgot your wallet or something at home. That robot might like to reason about the world and could use a hidden Markov model in order to do that. Let me explain what that might be like. Let's imagine that in your apartment you have a few rooms and your robot is going to move around that house and it needs to keep track of where it is. Now, the robot being inside, perhaps in an apartment building with many floors, maybe in an area that is high density, doesn't have access to GPS, and so it's not able to localize itself using satellite systems. And so instead, what it's going to do is it's going to try and localize itself by taking pictures of the floor. And by taking pictures of the floor, it's going to keep track of where it could be. And by adding an understanding of the layout of the room and how it's moving through the world, it will be able to reason about where it is based on what it sees currently on the floor and what it has seen previously in other camera shots of the floor when it was in other locations. So as the robot moves through the world, it'll take different pictures of the floor, and from that sequence of observations, remember, a hidden Markov model is a model that explicitly deals with sequential observations. From that sequence of observations, the robot is going to make a guess about where it is. So for example, it might start in this area of the home with a particular kind of gray floor. It might move and still see gray floor. It will move again and see a combination of gray floor at the beginning, maybe some kind of wood floor, maybe linoleum, and then finally some kind of a carpet or a welcome mat. And over the course of that movement, a combination of understanding the geography of the room, how it can move, and what it sees, it's able to take a guess about where it is. Now, in order to do that, it has to have some idea about what kind of floors there are. So in this case, we have 7 different floors represented. But it also has a way to represent its location. And when we represent the location, in order to make it amenable to the hidden Markov model, we're going to represent the location as one of, I think there's about 53 dots on this diagram. Each one of those dots represents a state that the robot can be in. It can occupy one of those dots at a time, and it must be on one of those dots. This is also a state transition diagram, and so you see that you can move from one state to another, but you can't move from one state to any other. You can only move to the states that are adjacent to you, that the robot is adjacent to, and that aren't blocked by a wall or furniture or some other impediment to the robot's movement. So it might move from this state up to a corner and then across the apartment to the door. In that sequence of motions, it'll traverse many different states. In each one of those states, it will observe a different floor. Now, of course, it's not exactly on any one of those states. These states are modeling an approximation to where the robot is. It can be, in that general vicinity. The state is going to be the best guess of where the robot is at a given moment. Okay, so we had a formalism for the hidden Markov model. How does that apply to this particular domain? Well, we know that a hidden Markov model requires 5 different components in order to describe it: n, m, a, b, and pi. And when we're reasoning about the world, we take a sequence of observations, represented here as O1 through OT, O capital T, where capital T is the total number of observations that are made during a particular run of the robot. So how do these different parameters map to what we're seeing? Well, for starters, the parameter n refers to the number or description of all the possible states. So in this case, the states there are about 53 of these states, and each one represents a different location on the world. So that's m. M represents the language of observations that can be made. And so we're talking about a discrete hidden Markov model, And so the observations that can be made must be drawn from a kind of symbol, a list of symbols, a vocabulary of symbols. If we were doing language modeling, those might be words. If we were doing speech recognition, they might be the sounds, the phonemes that you make when you speak. In this example, the observations are going to be the 7 different floor types we can observe. That's M, 7. A represents the state transition matrix. It gives a probability of being able to move from one state, I, to another state, J. And so in our graphical representation, this was represented by the states and the arrows between them. So in this case, the upper left state can transit to 3 other states, presumably with a 33% chance in each case. Not all states can move to all states. In that case, the transition probability would be 0. Next, a hidden Markov model has the parameter B. B is the distribution of probabilities, it's a probability distribution, of seeing one of the observable symbols given that you're in a particular state. And so in this diagram, what I'm showing is that when you're in a particular state, you have a particular distribution of what symbols you're going to see. So in this case, it's kind of a distribution by the entrance of the apartment. Small chance of seeing the welcome mat, a larger chance of seeing a tan floor. Now this distribution is different for every single state, and we represent all of those different distributions, each one associated with a state, by the set B, capital B. Finally, we have a parameter pi. Pi is the probability of beginning in a particular state. So when the robot starts moving around the world, it has to have some kind of a guess of where it starts. And so maybe this would be a very high probability of the robot starting by its recharging station. That would be sort of a reasonable example, a reasonable estimate for this particular model. Okay, given that we have a Markov model that is defined by these different states and these different probabilities, well, that gives our robot a way to reason about the world and a way to solve different problems that it might have about localizing itself or figuring out where it is. That introduces 3 key problems. These are the 3 key problems that we want to solve using our hidden Markov model. The first one is asking the question, what is the probability that a model generated a sequence of observations? You have a sequence of observations O, and you'd like to know what the probability is that a given model, lambda, generated those observations O. And for the rest of these video tutorials, I'll be using lambda as shorthand for alpha, beta, and pi together. Those are all the probabilities that are in our model. The structure of the model isn't part of that, just the probabilities that are in there. The second key question that we want to ask is what sequence of states best explains the sequence of observations that we've made. In this case, we might see that we've seen several different floor types as we've moved around the apartment, the robot has, but trying to understand which particular state it's in is non-trivial because in a given state, in several states, you can see the same floor types. So the second problem is trying to determine what was the sequence of states that you went through in order to see the observations that you did, or what's the most, in some sense, what's the best explanation for that sequence of observations. Finally, given that we have a set of observations, how can we learn the model probabilities that maximize our likelihood or our probability of generating a particular set of observations? This is the learning problem. How do we learn a model? How do we learn the parameters A, B, and pi so that we best explain the observations that we have? Let's tackle that first problem in this lecture. That first problem, what is the probability that a model generated a sequence of observations, can be represented as the probability of a set of observations given lambda. Now, why might you want to know this? Well, one way in which this can be used is trying to understand which model generated the observation. Which model best explains the observations? So if it's the robot case and the robot's moving around and the robot maybe doesn't know what apartment it's in, you have several different apartments with the same layout but different furnishings, the robot, by observing the different floor coverings as it moves through the world, can come up with a guess of whether it's in apartment 1, 2, or 3. This is a little bit a little bit of a contrived example, but a different way in which this could be used is trying to understand whether a particular sentence was written by an author. That would be a different way in which you could answer the same question. All right, so that means that we're going to need something called the forward-backward algorithm. The forward-backward algorithm is a way to solve this particular problem, the problem of finding the probability of a sequence of observations given a particular model. Now, if we run this algorithm 3 times, we can compare 3 different models with the same set of observations and ask which one of these models does the best job of explaining these observations. All right, let's talk about how we can get there. So let's start by imagining all possible state sequences that we might go through. So we assume that we have some number, capital T, which is the number of observations that we've made. And each time we make an observation, we know we're in a particular state because of the way a hidden Markov model works. And as we make one observation at time 1 and then another observation at time 2, we're also moving through a sequence of states, Q1, Q2, Q3, up to Q2. Now, as we move from Q1 to Q2, we may actually be in the same state, but Q1 represents the state we're in at time 1, and Q2 represents the state we're in at time 2. So if we think about the entire sequence of T states that we might have gone through, we can imagine all possible state sequences. Now, we're going to use this for purposes of reasoning. Of course, this is a very large number of state sequences, because if our robot was moving through the apartment and we said there were 5 sequences, five observations that were made, we would have to enumerate all possible combinations of 5 state sequences within that entire apartment. And that includes the state sequences that don't necessarily have a non-zero transition probability between them. So it's a combinatorics problem, all possible combinations of states. We're going to start there because that helps us with our reasoning and working up to our solution. All right, so what is the probability of seeing an observation, seeing the observations that we have, given that one particular sequence of states? Well, we can represent that with this equation. The probability of our observations, given our particular sequence of states that we're committing to, and the model that we have, is equal to the product of the probability that we saw, the particular observation that we saw at time 1, given that we were in the state we're asserting that we're in at time 1, and the model as well. Okay, so we're not reasoning about the different states we're in. We're given those states, and because we know which state we're in at each time, we know the probability of seeing the observation at that particular time because our model contains B, the probability of seeing an observation given a particular state. So this large product of 1 to T elements actually can be written in terms of a parameter that we've already seen in a previous lecture. Graphically, what this looks like is a sequence of states. Here we have 4 at the bottom of our slide. And in each one of those states, we observed one of the floor types. And we can look up what the probability is of that floor type given that state from our B parameter. So this becomes a very straightforward lookup and calculation. We multiply the probability of what we saw given the particular state sequence. Now we have a parameter that helps us to understand that. That's the lowercase b parameter. So we can say that the probability of an observation, given the states that we're committed to and the model that we've committed to, is simply the product of b sub qi, looking up observation 1, b sub q2, looking up observation 2, all the way up to b sub qt, looking up the observation at time ot. That first parameter, bqi01, is a function that tells us what is the probability of seeing observation 01 when we are in state Q1. And so that's like saying, what is the probability of seeing the welcome mat when we're by the door? What is the probability of seeing the welcome mat when we're by the kitchen? That is the number that we're looking up. All right, so again, this is the probability of seeing the observations given a state sequence. Now let's consider a different probability, a different calculation we want to do. This is the probability of seeing those state transitions that we've committed to given the other parameters in our model? So we can answer that as well. What is the probability of seeing a particular sequence of state transitions given our model? Well, we know that it starts with the probability of being in a given state at the beginning of our sequence. That's pi sub qi. All right. Well, what's the probability then? How do we increase that probability? How do we expand that probability to include the second state? Well, we say the probability of that would be pi I times the probability of transitioning from Q1 to Q2. So pi Q1 times pi Q1 times AQ1 Q2. That's the probability of starting in Q1 times the probability of moving from Q1 to Q2. Well, we tack on to the end of that the probability of moving from Q2 to Q3 all the way up until we get to the probability of being in state Qt minus 1 and moving to state Qt. This gives us the probability that we're going to move through the apartment in some particular way, the way that we've committed to when we were enumerating all the different state transitions, capital Q. All right, so we have an expression that says what's the probability of seeing a particular set of observations, and we have an expression that says what's the probability of seeing a particular sequence of states. If we put those two things together, we can combine them and say, well, what is the probability of seeing the observations that we saw and moving through the state transitions that we're enumerating? So for one particular state transition, what is the probability of that? Okay, now at this point, actually in the previous point, if we have a 0 probability of moving from one state in our apartment to another state in our apartment, for example, moving immediately from the front door to the kitchen without going through the states in the middle, well, that makes that sequence of state transitions equal to the probability of that sequence of state transitions immediately goes to 0. So that calculation is over very quickly. But there may be other sequence of states and other sequences of observations that we would like to combine them together. And so we're asking the question now, what is the probability of given a certain sequence of states, what is the probability of seeing that sequence of states? And if we see a sequence of states, what is the probability of seeing the observations that we saw? And so we can combine those two things together as the probability of the observations. It's the joint probability. The joint probability of the observations and the states that we're enumerating given our model. That's sort of combining those two things together in the graphic down, let's see, in the graphic down here at the bottom. Down here at the bottom, we see that we're chaining together now both the observations and the transition probabilities. And so we can say that joint probability is equal to the probability of the observations given the states and the model times the probability of the states given the model. So we're just chaining these probabilities through. Well, we've already enumerated those two things. We have an answer for the probability of observation given our states and our lambda, and we have a formula for the probability of our state transition given our model as well. So we can calculate those two things by combining them. Now, the problem here, though, is that we want to know what the probability of our observation is given our model. And we don't want to have to think about what states we went through in order to see those observations. So although we have the ability to ask what is the probability of a given observation and state sequence given our model, we want to eliminate that consideration of state sequences. So we're going to marginalize over all possible state sequences. So we're going to take the sum of the probabilities over all of the different possible state sequences of seeing those observations given the sequence times the probability of seeing that sequence itself. So if we sum over all the possible enumerated state sequences, we're able then to get the probability of our observations given our model. Okay, and that was what we were looking for. That was the solution to the first question. What's the probability of a certain set of observations given our model without committing to a particular state sequence? Now the problem with this is that although we can enumerate this very clearly in the following way, so the sum over all possible state transitions from 1 to capital T, it's simply the product of pi sub qi, the probability of starting in a state, times the probability of seeing an observation, O1, given that we're in state Q1, times the probability of moving from Q1 to Q2, times the probability of seeing observation 2, given that we're in Q2, times the probability of moving from Q2 to Q3, times the probability of seeing the observation in 3, 3 to 4, observation in 4, all the way up to t. So what is the probability of moving from state Qt minus 1 to Qt, and then seeing our final observation OT, given that we're in Qt? So this gives us the ability, if we're able to sum over all possible state sequences, the total probability, given the parameters of our model that we've got. It hopefully is a very satisfying kind of equation because it's the observations and the movement, the observations and the movement. It is, unfortunately, fairly intractable. Calculating this directly is infeasible. Well, why is it infeasible? Well, how many state sequences are there? Meaning, what are we iterating over in that sum? Well, if we say that we're going to consider t different different moments in our observation sequence, meaning t different states as well, and we know that there are n different states, then we're going to be summing over n to the t different sequences. You know, for example, say we had 2 states and we had 5 observations. The possible number of state sequences would be 2 to the 5th power. That is not very many, and it's growing very, very fast. Okay, so not only are we summing over a very large number of state sequences, but in each one of those sums, we have to do a large number of multiplications as well. We have to do 2 multiplications for every time step, except for the very last one, where we save one because we only have transitions between time steps, not for every time step. So we get 2t minus 1. So overall, what's the number of operations that we have to calculate in order to calculate this sum? Well, it's going to be 2t minus 1, the operation for getting one of the components of our sum, times n to the t power, because we have to do n to the t of them, plus nt minus 1, that's the actual addition for each of the components that we're calculating. That is not very good, because even with a fairly small model, for example, a model in which we have 100 time steps and simply 5 states, that gives us something on the order of, let's see, 2 times 100 minus 1, 5 to the 100, 199 times 5 to the 100, 5 to the 100 minus 1. We end up getting 5 to the 103rd power, approximately, or 10 to the 72 power operations. That is just not feasible. And this for a very, very small model. Well, that's the motivation for the forward-backward algorithm. We need a better way to calculate this, and the better way is the forward-backward algorithm. So hopefully that's motivating to you for why we need it, and in the next lecture, what I'll do is describe how we use the forward-backward algorithm to calculate the probability of observations given lambda in a time less than the lifespan of the universe. Thank you for your attention.